What specific problem does the proposed method aim to solve within the context of medical reasoning using LLMs, and how does this differ from existing approaches?
The proposed method aims to solve the challenge of enhancing complex reasoning in medical tasks using large language models, LLMs, by creating a dataset of 40,000 verifiable medical problems that allow for the verification of reasoning processes through unique, objective ground truth answers. This approach differs from existing methods, which often rely on traditional multiple-choice questions that do not necessitate deep reasoning and can lead to guessing. By employing a two-stage training process that combines strategy-based searches and reinforcement learning, RL, with verifier feedback, the method enables LLMs to develop and refine their reasoning capabilities iteratively. Additionally, the use of a medical verifier to assess the correctness of model outputs is a novel aspect that enhances the reliability of the reasoning process, contrasting with prior models that lack such structured verification. Overall, this method emphasizes the importance of complex reasoning and reflective thinking in medical decision-making, setting it apart from previous approaches that primarily focused on knowledge retrieval or simple task adaptation.
Can you provide a detailed breakdown of how the proposed method works, specifically outlining the two-stage training process and the roles of verifier feedback and reinforcement learning in this methodology?
The proposed method for advancing medical complex reasoning in LLMs consists of a two-stage training process. In Stage 1, the model learns complex reasoning by generating an initial chain of thought, COT, for a verifiable medical problem, which is then assessed by a verifier, GPT-4o, that provides binary feedback true or false on the correctness of the answer. If the answer is incorrect, the model iteratively refines its reasoning using various search strategies, such as exploring new paths or backtracking until a correct answer is achieved. Successful reasoning trajectories are then reformatted into coherent natural language and used to fine-tune the LLM, enhancing its ability to reflect and critique its reasoning. In Stage 2, reinforcement learning, RL, is employed to further refine the model's reasoning capabilities. The model, now equipped with complex reasoning skills, receives sparse rewards based on the correctness of its answers, guiding self-improvement through the proximal policy optimization (PPO) algorithm. This two-stage approach, combining verifier feedback in Stage 1 and RL in Stage 2, significantly enhances the model's performance on medical benchmarks, demonstrating the effectiveness of structured reasoning and iterative learning in complex medical problem-solving.
Can you walk me through a simple yet illustrative example of how the HuatuoGPT-o1 model generates a chain of thought, COT, for a verifiable medical problem, detailing each step involved in the reasoning trajectory?
The HuatuoGPT-o1 model generates a chain of thought, COT, for a verifiable medical problem through a structured iterative process. Initially, given a verifiable medical problem represented as a tuple, x, y caret asterisk, where x is the question and y caret asterisk is the ground truth answer, the model generates an initial COT, e_0, and an answer, y_0, using its initial reasoning capabilities. The verifier then checks if y_0 matches the ground truth answer, y caret asterisk. If the answer is incorrect, the model employs one of four search strategies such as exploring new paths or backtracking to refine its reasoning, producing new iterations, e_i, and answers, y_i, until a correct answer is verified. This iterative process continues until the model either successfully verifies an answer or exhausts its maximum attempts, ensuring that the reasoning trajectory is both reflective and adaptive to feedback.
What are the key advantages of the two-stage training approach employed in this method compared to traditional methods, particularly in terms of enhancing medical complex reasoning and its implications for practical applications?
The two-stage training approach employed in this method offers significant advantages over traditional methods, particularly in enhancing medical complex reasoning. In Stage 1, the model learns complex reasoning through a structured process that utilizes verifiable medical problems, allowing for iterative refinement of answers based on verifier feedback. This contrasts with traditional methods that often rely on simple answer selection without deep reasoning, which has been shown to yield minimal improvements. Stage 2 further enhances this capability through reinforcement learning, RL, where the model receives sparse rewards to guide self-improvement, leading to more robust reasoning skills. The combination of these stages results in a model, HuatuoGPT-o1, that not only excels in medical benchmarks but also demonstrates the ability to produce longer, more reflective chain of thought, COT responses, making it more applicable in real-world medical scenarios where complex decision-making is critical. This structured approach ultimately leads to better performance and reliability in medical problem-solving, which is essential for practical applications in healthcare.
How was the effectiveness of the proposed method validated, including the specific benchmarks used, and the metrics of performance that demonstrated superiority over existing models?
The effectiveness of the proposed method, HuatuoGPT-o1, was validated through extensive experiments on standard medical benchmarks, including MedQA USMLE test set, MedMCQA validation set, and PubMedQA test set. Additionally, the model was evaluated on challenging datasets such as MMLU Pro and GPQA, which require not only medical knowledge but also advanced reasoning capabilities. Performance metrics indicated that the 8B version of HuatuoGPT-o1 outperformed the base model, LLMA3, 1 to 8B instruct, by 8 points overall, while the 70B model surpassed other open-source general and medical-specific LLMs across multiple benchmarks. The results demonstrated that the two-stage training strategy, which incorporates complex reasoning and reinforcement learning, significantly improved performance compared to models trained solely on traditional medical multiple-choice questions. Furthermore, an ablation study revealed that the use of complex chain-of-thought, COT reasoning, contributed to an average performance increase of 4.3 points, underscoring the model's superior reasoning capabilities.
What are some identified limitations or challenges of the proposed method, especially concerning the reliance on verifier effectiveness, data quality, or potential biases in the training process?
The proposed method faces several limitations and challenges, particularly regarding the reliance on the effectiveness of the verifier, data quality, and potential biases in the training process. Firstly, the verifier, which is based on GPT-4o, achieved high accuracy rates of 96.5% in Stage 1 and 94.5% in Stage 2. However, its performance is still contingent on the quality of the input data and the inherent biases present in the training set. Secondly, the data set of 40K verifiable medical problems was constructed from closed-set medical exam questions, which may introduce biases if the selected questions do not adequately represent the diversity of medical reasoning scenarios. Additionally, the filtering process to ensure unique answers and the removal of ambiguous questions could inadvertently exclude valuable data, limiting the model's exposure to a broader range of medical reasoning challenges. Lastly, the reliance on a single verifier may create a bottleneck in the verification process, as any shortcomings in its reasoning capabilities could directly impact the overall performance of the HuatuoGPT-o1 model.